are now, yes, we are recording again. And so, Lorentz, his only purpose, and of course we have to still fix this up because right now the refractive index is blowing up on resonance. The only purpose Lorentz had was to include resonance somehow into the picture because there's so much interesting stuff that happens at resonance. Okay, what we'll find is that the absorption goes through the roof. The real part of the refractive index also does a weird number. In today's parlance, what happens is that the imaginary part of the refractive index ordinarily goes through the roof, but if you play things smartly and you know quantum mechanics, then you can actually you can make electromagnetically induced transparency happen, okay? And you can play with the refractive index right on resonance and come up with this absolutely wonderful effect, which people are using now for quantum information storage. The other thing is that the real part of the refractive index, right on resonance, again, if you know your quantum mechanics well, and if you can affect that new thing I was talking about, the electromagnetically induced transparency, then you can come up with you can actually create, in the real part of the refractive index, something that gives rise to extremely slow speeds of light, and extremely slow, like, I mean, a millionth or a billionth of the speed of light in vacuum. So there's all kinds of new things that can be uncovered from this formula. But Lorentz was only interested in, and that's why Lorentz was interested in resonance, because everyone knew that on resonance you can have magical things happen. But there are other very interesting and unexpected successes from the Lorentz model, which I am sure that you will like to listen to. And so let's just look at those. So this is, did I include that other page in there? Oh, I said that was 2.5. Well, that's wacky. Let me just fix this. So that's 2, this is 3, and then that would make this guy 4. Okay. And so then all right. So yeah, this is kind of cool. So let's do unexpected interesting, yeah, successes of the Lorentz model. And just tell me when I hit 3:35, please. I'm 5 minutes away, I understand. And what are these? Well, the first thing is that we will be, for example, we can now understand why metals are shiny in the visible, for visible frequencies, okay, for visible frequencies, but metals are transparent to UV. Okay, so we'll be able to see that. The other thing is that if you've ever tuned to stations that are outside your local region, I mean, one thing is that all the local transmissions are so-called the frequency modulation, FM. Okay, the FM band, and and the FM band is about 100 megahertz. Okay, so that's why you have the 98 PXY and the 99.9 WMUB and 91. It's about 100 megahertz. That's what And then there is the AM band for long distance. So this is for long distance communication. You know, when I was in India, we used to tune into BBC sometimes for cricket matches, for the World Cup and stuff. And so that is that is like less than a megahertz. Okay. And so, so this is used for long distance communications, and there's a reason for this. That why do you have to be, only these low frequencies will be able to travel over long distance. Meanwhile, these frequencies are only good for local transmission. Okay, and there's a interesting, and the answer to both of these is connected, believe it or not, um, because it turns out, now this is where, you know, physicists see all these connections, and it's really cool because it turns out that both, you know, so this communication and all this has to do with the Earth's ionosphere. And you know, the Earth's ionosphere is basically a layer. So I mean, if you you know, let me make sure. So if you have the Earth, right, and then above the Earth, there is you know, the troposphere and the stratosphere. Well, there is a band, there is a layer where the air molecules have been ionized by solar radiation, and so there is a certain like density of these ions, and then as you go above, then there's just less atmosphere to be ionized, and as you come down this way, then solar radiation does not get down in sufficient quantity to be able to ionize stuff here. So there's this sweet spot, okay, where you have the ion. So this is the ionosphere layer, okay. And so there are free ions in there, free charges, okay. And it turns out that it's not too different from metals, which are, of course, free electrons. There's a lot of free electrons in the metal. Okay, so free electrons. So the point is that when you have free charges, okay, and it's a sort of a dilute collection of free. So what's the common theme here? So this is actually, you know, they're both plasmas. Now, what's a plasma? A plasma is defined as a collection of free, meaning weakly damped, free charged particles. Now, granted, in a metal, the density of these electrons is going to be higher than the density in the ionosphere, but they both have this in common, that they are a plasma, okay? And so what I'm telling you now is an unexpected success of the Lorentz model in a plasma, okay? So the first thing is that what happens in the plasma is that if you look at the original Lorentz model equation, which is right here, okay? So the first thing that happens is that they're free. So they're not really bound, all right? So the omega naught, so this, because of this thing here, they're not really bound. So the omega naught is 0. There is no, I mean, it's almost 0. So now if you look at the solution that you have, which is this, okay, which is this, n is that. So now the refractive index for the plasma, and I'm just using that same solution, is square root of 1, right? And the omega naught goes away, so you're left with a 1 minus NE squared over M epsilon naught 1 over omega squared, right? And what people do is that they'll take this guy right here, and they, because you know that this has to have the dimensions of frequency squared, right? They call it the plasma frequency squared. So plasma frequency squared divided by omega squared, that's dimensionless as it should be, and then 1 minus, and that's your refractive index of the plasma. So this refractive index of the plasma is written as 1 minus omega plasma squared over omega squared. Okay, and so that's what they do, and this is, so where, let me be just clear, that omega plasma is equal to the square root of NE squared over M epsilon naught, right? And this, of course, you can write it as 2 pi nu p, okay? This guy here is the plasma frequency. And now things are going to make a lot. So I could also write this as equals square root of 1 minus nu plasma squared over nu squared, right? The 2 pi's would cancel. All right. Now, there's something very interesting in here. Notice how this is 1 minus that, right? So what this is saying is that, note, are you ready for this? This is where the exciting part starts. Note, oh, and wait a minute, am I 338 already?
Not at the exciting part, Dr. Belly.
Well, yeah, this is the exciting part. So if you'll allow me to go just a little bit over, all right? So do all those in favor of Samir sort of violating his promise and going ahead, spending 5 more minutes, please say aye.
Aye.
I heard 3 ayes, and the ayes have it. Well, because is there anyone saying nay? See, the nays are just too polite. I mean, they'll never say nay. Even though someone could disguise his voice and say it, and I would never know who it is. But yeah, the nays are just not gonna do it. So okay, so the 3 ayes have it, and so if I promise you, this you will like, because please note that if the plasma frequency ever happens to be, so if your incident frequency happens to be less than the plasma frequency, what happens to the refractive index? The refractive index is purely imaginary. Purely imaginary. What that means is that it gets, remember, if it's imaginary, it all gets absorbed. It's all absorption. So this is interesting. The refractive index becomes purely imaginary. And the other thing is that the plasma frequency depends on the medium. Like, for example, I mean, it's the number density, electron charge, mass, epsilon naught. So I can actually work it out so for example, if I look at, let's do the metals first, all right? So, so this is interesting, because if I do metals, let's just do copper, okay? And I can work out for copper what the plasma frequency is, okay? And I have the numbers here. I have, so it's 1 over 2 pi square root NE squared over M epsilon naught, and I have the numbers 1 over 2 pi square root. The number density I have as 10 to the 29 per meter cube. Very dense, you know. It's a solid state medium. So And E squared is 1.6 times 10 to the minus 19 coulomb squared, right? The mass we know, 9.1 times 10 to the minus 31 kg, so it's all SI units. And the epsilon naught, I looked this up, 8.85 times 10 to the minus 12 SI units, right? And so I worked this out, and this gives me 3 times 10 to the 15 hertz. Okay, now here's the kicker. So if your visible frequencies, what are your visible frequencies? The visible frequencies are, nu goes from 4 times 10 to the 14 hertz, and that's red, okay, to, and let's color code it, 7 times 10 to the 14 hertz, and that's blue, right? So, but you notice that it's always, this stuff here is less than nu p, the plasma frequency. So that's why the visible frequencies are very strongly absorbed, because purely imaginary means that strong absorption. Okay, so these are strongly absorbed, so which implies visible frequencies strongly absorbed. All right. Now, how does that mean that it's shiny? Because strongly absorbed. So normally in this class, like in 600 ENM, we actually prove that if something is a strong absorber at a certain frequency, that means it's a very strong reflector also at that frequency. Reflection happens at the surface, absorption happens in the bulk. This is a very interesting property of materials. It's counterintuitive. It shows up in the math. In this class, laser physics class, I actually used a demo to show that. I'm going to, what the hell, I'll try and do the demo on Tuesday. And especially, people like Ben, or anyone, or maybe Scott, who have worked with dyes, would truly appreciate it. So I will talk about this fact next on Tuesday. Strongly absorbed also means that they are strongly reflected. And that's why it appears shiny. Metals appear shiny. Okay. On the other hand, UV light, the frequency is 10 to the 16 to 10 to the 17 hertz, which is greater than the plasma frequency. And so therefore, there is a real refractive index, and they're transparent. And of course, there is something interesting there too, that even though the refractive index is real, you'll notice it's less than 1. And so UV light, I mean, what does that mean? And I don't have a quick explanation for that, but it does dip slightly below 1, and you do get transparency. Okay. But mostly what you'll notice is that for UV light, it actually, this is quite, it's much smaller than 1 also, right? I mean, the nu is, yeah, I mean, so this is like a 1 over 100. So it's 1 minus 0.01. So it's a small dip under 1. But still, that's kind of worrying, because what does that mean for the speed of light in the medium? You can't possibly mean that it's traveling faster than the speed of light. So it's not quite accurate, but it tells you that it's real. Okay, that part is accurate. The atmosphere, let me just talk about it Next time when I show you the demo, and the demo will involve dye particles, and we'll deal with that. So and then I'll talk about the atmosphere and the ionosphere at that time. Okay. Um, so there is some unfinished business here. We shall deal with that next time. Um, okay. So any questions so far? To give you a sneak preview, we will learn about the AM/FM. I mean, what I can just tell you very quickly that the plasma frequency for the Earth's ionosphere works out to 9 megahertz. And so you can see the frequency, the FM band is comfortably above it. And so that means the ionosphere is transparent to the FM band. But the ionosphere is a very good reflector because it's not transparent, and it actually turns out that it reflects the AM band. And so you can just bounce between different points and go from one point to another very far off point. But let me talk about that next time. Okay, so we learned that, and then we can also from this learn this really important principle that all good absorbers are good reflectors. We can also, and then we will learn about why things appear green underwater, the blue sky and the pink sunset. We can do that on Tuesday. So that's our plan. I might have to leave a couple things out because I did want to get to, well, we might just leave out well, the whole point was to talk about fine hyperstructure, the fine structure of the hyperfine structure or the spin of the nucleus. And I'm just wondering how motivated you will be to go into the theory for saturated absorption spectroscopy, given that you couldn't actually do it in the lab, and that's, so that's a bit rough. So we'll just see what we can do, and some things will have to just be left out. Well, I should let you guys go at this point. If anyone has anything to say or ask, please hang on. Otherwise, please feel free to say our adieus at this point.